Okay, up until this point, we've been kind of categorizing everything and giving specific rules. So today is going to be more of a general situation. We're going to establish general rules for addition and multiplication. And then we're going to end up talking about the law of total probability. We got quite a bit of ground to cover. Those 3 rules and then 10 examples. So, first, let's look at the general rule. Naturally. There we go. Okay, so first let's look at the general rule for addition. So let's say we have any 2 events, E and F. Then the probability that E or F occurs is the sum of their probabilities minus the probability that both occur. Now, you may be asking, why are we taking out the probability that both occur? Does one or the other occur then?
That would be double.
I'm sorry. So, let's look at this Venn diagram. We have E occurring, so there's that circle. F occurs. Well, how many times did I just shade in the middle here? Twice. I don't want to count these twice, I only want them once. So I have to subtract out one of the intersection. That way we're not counting them twice. And one thing you could even do is just remember this rule. If they're disjoint, meaning they don't overlap, what would this number be right here? 0. So we learned about the case where they were disjoint already, and this was 0. And now we're like, okay, well now it's not 0, it's an actual number. But even then, it's up to you.
I'm assuming it'll be beneficial.
I mean, if you're a visual person, it might help you.
Thank you.
So if you're like, okay, I just want to remember one rule for addition. I don't want to have to remember what 2 cases and all that stuff. Then just remember this one. Because if they're disjoint, meaning they don't overlap, this one's just going to turn into a 0. Okay. So since we're trying to get it written down, so I'll hold up for a second. Let's look at our first example for today. In all of our examples, I'm going to work it with y'all instead of clicking through the PowerPoint. Okay, so first example, Says music styles other than rock and pop are becoming more popular. A survey of college students finds that the probability they like country music is 0.40. So what I'm going to do is, as I'm reading this problem, I'm going to make note of that. So probability that they like country is 0.4. The probability that they like jazz is 0.3. And the probability that they like both country and jazz is 0.10.
Can we abbreviate or?
Yeah. What's the probability that they like country or jazz? So we have to find the probability of country or jazz.
So downward means, or like the upside down U means and the right side up U means or.
Then this means or. This means and.
All right, thank you.
Uh-huh. So we have to use the rule that we just talked about. The probability of country plus the probability of jazz minus the probability of country and jazz. At this point, we just plug in. So the probability of country is 0.4. Probability of jazz is 0.3. Minus the probability they like both, 0.1. So what would this be equal to? 0.6. So the probability they like country or jazz is 0.6. So I want y'all to take about a minute or so, try to set up that next one. Let's see if you can set it up and work it.
To be honest with you, Schultz, I forgot which total we were supposed to use. Like, to just the, we're supposed to be doing something else. Like, when you do like this number divided by total.
What's
Oh, it's already got the probability, my bad.
that one probability of column or satisfied?
Oh, or, okay, I got you, so. Probability of being
That's right.
So like the probability of college would be 1.5 total, and okay. I understand. Thank you.
Yes.
It's in my bad. Yeah.
The only one that's probably that they're college or satisfied, right? So we would have to write it first, if we think back to our formula that we just learned, probability of C or S. Yeah, we do, we need all three of these. We're gonna solve it however we do this one. Is that right?
College.
I did. Oh, just that one, okay.
Satisfied.
You're on the right track. What you got? Yesterday we said they weren't. Or, yesterday, you said they weren't, sorry. You said they weren't. Okay, so if they're independent, only thing we can do is see if they're independent. We can multiply these two, the total for satisfied, times the total for college. If they're independent, then this product should give you that one. If it doesn't, then that means
You can just. Yes. This number. Mine is being copied and satisfied. That's where these two intersect. So I said it's number one. Number one.
College and satisfied. Okay. Let's look at this one. Can't kill too much time, so I'm gonna go and talk through it.
Do we need to round?
I don't think we should have to round on this one.
Okay.
No rounding needed.
Cause I got .66003.
That's right.
I was just checking.
Okay, so find the probability of a teacher teaching at the college level or being satisfied. So we want the probability of college or satisfied. That's what we're wanting to find. Now they ask us, are C and S dependent? What was a quick way, I said yesterday, if we're given a table that we could test for independence? That's right. So, if I did probability of, I'm writing these backwards, but, okay. lovely. My computer is frozen. Don't tell me it's doing this weird thing where I've got to shut it down again. Okay, that works now. I was starting to sweat it here. So we could multiply their totals. I'll go on and say yesterday we already proved that they are not equal. So are these dependent? Yes, they are. Okay, we saw that answer the original question. They want us to find the probability of C or S.
Mr. Schultz,
Yes.
is it asking if the shoot of the events, is it between 0.6 and then 0.0951?
Repeat that, please.
Sir?
Can you
Oh,
repeat
sorry.
that, please?
What are the two different events? Like, is it just C and S?
Yes.
Okay. Like, could you elaborate on how it's dependent? Like, I don't disagree, but like, I'm just curious if,
Like, what's the connection between the two? Or
what makes them dependent? Like, what are the numbers?
okay, let's see. Let's see what this. I'm trying to think of a way to word it. So how can we get? Are you asking how can we make this jump to say they're?
Yeah, like what numbers make it dependent?
Okay, well, when we multiply these two together, if they were independent, this product right here, which is, let's see, point. So this product right here gives you 0.0828. That's what we found yesterday.
Okay.
If they were independent, these should be equal.
Okay.
So
we had to multiply them?
Yeah.
Oh, I didn't know anything. Oh, that's to find out if they were dependent.
Yeah.
Okay, I got you. My bad.
Yeah. This was to answer that little first question right there.
I understand. I just get a little confused.
Okay, so using our formula, probability of C plus the probability of S minus the probability of C intersect S. So the probability that their college is 450 plus the probability, wait, no, that's the probability that they're satisfied. We'll go with it. Just know this goes with that one. Probability that their college is 0.1504. This goes with that one. Minus the probability that they're both 0.951. So then we would type that in and we should have gotten 0.6003. Don't make that an E. Okay, questions on this one? No? Let's see, so I'm trying to write it down, so I'll wait. That's not cool. Okay, so we just did these two examples. So we can actually use a process to figure out which formula to use if we're calculating the union of two or more events. So let's say we have events E and F, and we're taking the union. We have to ask, are they mutually exclusive? If you say yes, they are, meaning they have nothing in common, then we just add their individual probabilities because they have nothing in common. So there's nothing to subtract out. Now, let's say we answer no, they're not mutually exclusive. Then we would have to use the formula that we just learned, where we subtract out their intersection.
So if they're independent, they would be mutually exclusive.
Not necessarily. Nope. So in some problems, we give you the intersection of the events, like we did in the previous two examples. In others, the intersection isn't given, but we know that they're independent. So if they're independent, we can find it by multiplying the two probabilities to get the intersection. We can only do that last step though if they're independent.
So what if you're dependent and you're not given the probability to intersect that?
Well, you would have to try to use some of the other formulas that we're about to talk about to see if you can figure something out. If you still can't figure anything out, then you don't have enough information. Okay.
This is to do what again?
This is to calculate the union of two or more events happening.
What's the union?
Or.
Okay.
Yes, Will.
What does it mean, like, when events are mutually exclusive, what does that mean exactly?
So mutually exclusive means that they have nothing in common. So, like if I rolled a die and then flipped a coin, is there any way I could get the same result on those at the same time? No. So those are mutually exclusive. They have nothing in common.
So basically, you know, like for it to be, have something in common for them to be the same object.
Same object, or like if you're doing a combination of the objects. Like let's say we're buying DVD players and we're told they're going to buy 2 or 3 of them. Well, then they could buy 3 of the same DVD players, so they would have something in common. Does that make sense? Okay. Okay, next example. We have 2 separate die here. So we have a we have 2 6-sided dice that we're going to roll. One is red, one is white. What's the probability that the white die lands on a 6 or the red die lands on a 1? So let's look at these. Okay, so we're going to say A is where the white die lands on a 6. B is where the red die lands on a 1. Or A and B disjoint. So they can't happen at the same time? These are not disjoint because they can happen at the same time. They're 2 different die, so they can happen at the same time. So since they can happen at the same time, we said no. That means we have to use our new formula that we just learned to find the probabilities. So the probability that A occurs plus the probability that B occurs minus the intersection of the 2, that A and B occur. Now, this question isn't on here or in your notes, but let me ask you this. Are A and B independent? Yes. So are A and B independent? Yes. So what that means is when we find this intersection here, it's just the product of their individual probabilities. So what's the probability that A occurs? 1/6. What's the probability that B occurs? 1/6. So the probability that they both occur would be 1/36.
And that's to find out if it's independent.
Well, we know they're independent because we have two separate die here. We have a white die and a red die. So we know they're independent.
And independent basically means like they can both change on their own, like they don't need each other. Okay.
Okay, so to find the union, we go back to our original question. We already said the probability that A occurs is 1/6, plus the probability that B occurs is 1/6. And then we just found out that the intersection is 1/36. So what's the probability that one or the other occur?
Are we supposed to do a fraction form or?
Let's do fraction on this one.
So,
11/36. Questions on this one? Okay, on to the next topic then. So now we have the general multiplication rule. So we talked about the general addition rule. Now we're doing the multiplication rule. If we have any two events E and F, the probability that E and F occur is the probability that E occurs given F times the probability of F. And then due to the probabilities being symmetric, we can also do the probability of F given E times the probability of E. Either one will give us the probability that E and F both occur. Oh, go back.
What does the line mean again?
Given.
Okay.
So like that P, the first one, probability of E with the line and then F, that means the probability that E occurs given that we already know F has occurred.
Yes, sir.
Kind of like, as far as football goes, the probability that you win given you score first.
Okay, I got it.
Okay, let's look at the process to use when calculating the intersection of two or more events. So you have to ask yourself, are they independent? If you say yes, well then that's easy. Just multiply the probabilities. Are they independent? Sure. Okay, fine. Just multiply probabilities. But if they're not, then we have to use our rule that we just talked about.
It's a lot of what if, or like not what if, but like yes or no type deals.
Mm-hmm. A lot of scenarios to bounce
Yeah,
around.
that's what it is, scenario.
Yeah. Okay, so let's look at another example. This is the secretary example. 18% of all employees in a large company are secretaries, and furthermore, 35% of the secretaries are male. If an employee from this company is randomly selected, what is the probability that the employee will be a secretary and also a male? So we're going to let E stand for the event that the employee is male. F is the event that the employee is a secretary. So the question can be answered by noting that the probability that F occurs where is my point at? There it is. Probability that F occurs, so events of secretary, employees and secretaries, 18%. Probability of E given F. So E is that they're a male. So male given that they're already a secretary, 35%. Okay, so let me go back to here. So So we said we can note that probability of secretary is going to be 18%, and probability of male given being a secretary is 35%. And they ask us to find the probability of being a male secretary. Probability of E and F occurring. So we have to use the rule that we just talked about. Probability of E given F times the probability of F. 0.35 times 0.18. What would that get you? Yep. So that's the probability of being a male secretary.
I thought the question was asking for the or.
No. Be a secretary and also, that's a horrible circle.
And also no.
And also male. And, yes. Yes.
So how do we know if this one was independent or not?
If it was what?
Independent or not, just example.
Let's see. Honestly, we don't know whether or not it's independent, but even, let's say it was independent, then you could still find this because the probability, if it was independent, this would just be the probability of E here instead of E given F. If they were independent, these two values would be the same.
But they're independent.
They don't tell us if they are or they're not. So we're going to just assume if they don't tell you they're independent and there's no reason to assume they're independent, we're just going to assume they're dependent.
All right.
Does that make sense?
Sure.
And plus, if you just note what they give you, then it's also easy to tell which formula you use. If you know your formulas, like, oh, they give me this, I'll just use that formula. Okay, so let's look at the next example. So there's 7 girls and 8 boys in the math class. The teacher selects 2 students at random to answer questions on the board. What's the probability that both are girls? Now, we're gonna assume here that they're going up to the board at the same time. So one's going to one side, one's going to the other. They're going at the same time. Would these events be independent? let's see, if G1 is the event that the first one is a girl.
That's independent.
You said dependent or independent?
I mean, I'm just guessing which one, right? I would say dependent.
Dependent?
Yeah.
Well, okay, so if one's a girl, they go up there. Will that change the probability that the second one's a girl?
That's what I'm saying, because like, if there's one already up there, then you can't, there's less than girls to pick from.
Exactly. So are these independent?
No.
No.
You just gotta think about that.
You just have to think about it. Okay. So G1's the event the first one's a girl. G2's the event that the second one is a girl. So the probability that G1 and G2 occur. Well, what's the probability that they pick a girl first?
Seven or 15.
There's 7 girls, 15 total. So 7 out of 15. Now, let's say the first one is a girl. What would the probability be of picking the next one? 6 out of how many? 14. So if we multiply those together, what would we get? .2. Yep. Questions on this one?
That's the whole thing?
Yeah, that was this whole example.
That's with or without replacement, correct?
This is without replacement. Yep. Okay, on to the next one. So we're going to go back to the light bulb example that we talked about at the end of class yesterday. So a certain brand of light bulb is defective 5% of the time. You randomly pick a package of 2 such light bulbs off the shelf at a store. So one package has 2 bulbs in it. What's the probability that exactly 1 bulb is defective? So do I want no bulbs to be defective?
Yes. Wait.
The problem says exactly 1 bulb.
Oh, I thought you were asking, like, overall, would you want?
Do I want 2 to be defective?
No.
No, I just want 1. So how could that happen? If D1 is the first light bulb is defective, D2 is the second light bulb is defective, how could I state an event that talks about only 1 being defective? So let's call it E.
No, wait, is this the, you multiply 0.95 times 0.05 plus 0.05.
So, well, if the first one's defective, Do I want the second one to be defective? No. Or I could have the first one not defective and the second one defective.
So the first one doesn't have to be defective.
On that second option, that's right. So the first option, the first one's defective, but the second one's not. And then we flip it.
And the seeming complement, right?
Yes. Okay, so I want the probability that E occurs. So the probability of E would be the probability of C1 being defective, but bulb 2 not, or bulb 1 not, and D2 is. Okay, so what's the probability that bulb 1 is defective on this first instance?
5%.
5%.
So 0.05.
0.05. What's the probability that bulb 2 is not defective?
0.05. Isn't it? Wait, not defective. Oh, 95.
That takes care of our first situation. Now let's look at our last situation. What's the probability that bulb 1 is not defective? 0.95. What about the probability that bulb 2 is defective?
0.05.
So if I multiply and then add, what would I get?
Why are we multiplying?
0.95 times 0.95 because the bulbs are independent.
Okay.
So I kind of left that part out. We assumed we figured out yesterday bulbs are dependent. Sorry, independent, not dependent. So what would you get if you calculate that? 0.095. Questions on this example?
One more look at it.
Okay, I'm going to go back to the PowerPoint. And we actually went through 3 examples, so I need to advance my slides. Boom, boom. Okay, so now we have an electronic store that sells DVD players made by one of 2 brands. Customers can also purchase extended warranties for the DVD player. The following probabilities are given. And so, if we let B1 be the event that brand 1 is purchased, B2 is the event that brand 2 is purchased, and E is the event that the extended warranty is purchased, then the probability brand 1 is purchased is 0.7, brand 2 is 0.3, the extended warranty with brand 1 is 0.2, and the extended warranty with brand 2 is 0.4. So if a DVD customer is selected at random, what's the probability they purchase the extended warranty? We're not going to solve this right away. We're going to use it to set up another theory, basically. So we can do this one of 2 ways. We can purchase the extended warranty with brand 1, or we can purchase the extended warranty with brand 2. So that's our possible event that can happen. The warranty with brand 1 or the warranty with brand 2. Those are our 2 options.
You go back real quick.
Yeah. Everybody looks like they're so tired today.
Almost done, man.
Almost done with the day, is that what, or
Yeah, over the week.
a week? Yeah. Next week, tomorrow's Friday. Okay. So let's look at the last new topic today, the law of total probabilities. So if B1 and B2 are disjoint events where their probabilities add to equal 1, then for any event E, the probability that E occurs is the probability that E and B1 occurs, plus the probability that E and B2 occurs. So if we want to find the probability of E, we have to consider E in all cases, basically. Now, we're going to use the multiplication rule that we talked about just a second ago to extend this. So the probability that E occurs is the probability that E given B1 already occurred times the probability of B1 plus the probability of E given B2 times the probability of B2.
There's a lot of stuff we gotta memorize in this one.
Yes, but tomorrow's a short day. tomorrow lecture will probably take 20 minutes. Assuming we get finished where we need to today. We're actually kind of behind third series right now. Time. Okay, so this can be extended to K events. So we did it with 2 events above, but we can extend it to K disjoint events. So taking the same concept, probability of E is equal to probability of E and B1 occurring, E and B2, all the way to E and B sub K. So expanding that formula out like we did the first one. Now, some of this dual credit may be on your formula chart. I can't remember. Some of it may be. Okay, so let's look at our DVD player example.
Can you go back one more time? Sorry. Come on, Luke. All right, thank you.
Uh-huh. Okay, DVD player example. So we're sticking with the same setup that we had. So if a DVD customer is selected at random, what's the probability that they purchase the extended warranty? Well, we already said that our event is where they do the warranty and they buy brand 1, or the warranty and they buy brand 2. We're gonna say these are disjoint events. They're not buying 2 DVD players, they're just buying 1. So, let's use the formula that we just learned. Probability that E occurs is probability that E and B1 occurs, plus the probability that E and B2 occurs. Using the law of total probabilities, we have the probability of E given B1 times the probability that they bought brand 1 plus the probability of the warranty given they bought brand 2 times the probability that they bought brand 2.
So these are just like both of the options.
That's right. That's exactly right. Looking at our formula that we have written out and the information given, hopefully you can see that they've given us everything we need. So E given B1, that probability is 0.2. The probability of B1 is 0.7. So 0.2 times 0.7 plus the probability of E given B2 is 0.4 times the probability of B2, 0.3. So if I do that arithmetic, what would I get? .26. Yep. That's the probability that E occurs. So this is an example that we just did. The law of total probability. Questions on this one? Let's see, I'm trying to write it down. Okay, next one. So now we have a soccer example. So a soccer team wins 60% of its games when it scores the first goal. 10% of its games when the opponent scores the first goal. If the team scores the first goal about 30% of the time, what fractions of the games does it win? So we're going to let W be the event that the team wins, and SF be the event that the team scores first. Before we do anything, let's just make sense of the probabilities they gave us. So, first thing it says is the team wins 60% when it scores first. So the probability of win given score first is 60%. 10% if the opponent scores first. So probability of win given not scoring first, 10%. And then it says the team scores first about 30% of the time. And it wants to know the probability that they win. So this is a law of total probabilities. We have to take into account all their situations here. And we're going to say by the law of total probability,
You have to say this out.
you don't have to what?
You have to say this
I would like you to.
Write it down.
Yes. By the law of total probability. This is how we're going to work the problem. So the probability that we win equal to the probability of win, given we score first, times the probability that we score first, plus the probability that we win, given we do not score first. Times the probability that we do not score first. Okay, so let's plug in. Win given score first is 0.6. Probability that we score first is 0.3. Plus the probability of win given we did not score first. 0.1 times. What's the probability that we did not score first?
10%.
What's that?
Oh, wait, yeah, 10%.
0.7. The probability we scored first is 0.3.
What's that for?
So second line, almost at the end. If the team scores the first goal about 30% of the time,
Okay. Oh, 0.3, I got you.
yeah. So not score first would be 0.7. So if we work this out, what's the probability that they win? Point 0.25. And I don't think we have two more examples. I think we're probably only gonna get to do one, and then we're gonna have to stop and just catch up tomorrow.
Okay.
Questions on this one? There shouldn't be. We've done enough. There shouldn't be. That one just has a lot of reasoning in it. That's the only reason it takes so long, because there's a lot of
It
reasoning.
looked pretty complicated, so that's why that was confusing.
Yeah. Okay, so let's look at this chess example. You enter a chess tournament where your probability of winning a game is 0.5 against beginners. Wait, no, 0.3. I can't read. So the probability of winning against beginners is 0.3. know how this problem works, because everything in here is backwards. I'm just using the numbers they give. Yeah, it does not make intuitive sense. The probability that you win against an intermediate player is 0.4. The win given intermediate is 0.4. And then the probability that you win given their advanced is 0.5. Maybe you like the challenge and that's the only way you thrive is if you're challenged. Otherwise you get bored and distracted. Half of the players are beginners. So what's the probability of beginners then? 0.5. A quarter of the players are intermediate. The probability of intermediate, 0.25. And a quarter of the players are advanced. Again, 0.25. So you're going to play against a randomly chosen opponent. What's your probability of winning?
Wouldn't you do that, but it'd be like +1,
What do you mean?
You'd like do the same thing we did for the other ones, but instead of just doing 2, you just do.
Yep, that's right. So what's that law called?
Law of total probability.
Yep. By the law of total probability.
Long equation.
The probability that you win is equal to the probability of win given beginner times the probability of beginner plus the probability of win given intermediate times the probability of intermediate plus the probability of win given advanced times the probability of advanced. So then we can just go through and plug everything in. 0.3 times 0.5 plus 0.4 times 0.25 plus 0.5 times 0.25. So the probability that we win is what? 0.375.
Pretty good chance.
Unfortunately, we did not get to finish, so we're going to start one problem behind tomorrow, but we can catch up.
Is this on the homework?
Is this day?
Yeah.
It should be on the one that's due Friday. It'll be on the one I give y'all tomorrow.
Okay.
And then AP, we're gonna have y'all's day will be short tomorrow. Dual credit, I'm sorry, y'all's day won't be as short.
Will it be relatively long or what?
Wait, what is not gonna be the same?
Well, y'all have
Our
one.
assignment? You know about our assignment?
No, y'all actually have another topic that we need to talk about. That they don't cover in AP. Because they've already had geometry. Most of you have. So we gotta cover a topic.
And here.
They can take a long time.
So you
Like, I can wake up 30 minutes earlier.
Until I want to get the energy and motivation to stand up, get dressed.
I feel like lots of this probability are given B.
Yeah.
Remember that?
We had almost,
That's not.
Can I go to?
That makes a lot of sense. It's like 5 hours. Back to you before.